Hello friends, welcome back to my channel. So today, uh, this video is a mix of concept and problem solving sessions. So what we'll be doing in this video is I will be teaching you some concept, especially a branch concept, and I will leave you with some problems for those concepts to be applied in them. So let's begin. So today, if you remember in the last video, we talked about methods, one method especially to solve or to find integer solutions to equation, those factorization methods and all. I gave you a lot of problems on that. So now this method will be, this video will be on how to prove that there exist no solutions to an equation. So let's begin. So there are many ways to prove the. So our main motive would be to let me change the color, to prove no solution to an equation. So this will be a motive. So how to prove that there are no solutions to an equation? So there are multiple ways to do so. Now we will be talking in detail about each and every way. So the ways are, first of all, the first way is uh, factorizing method. Factoring method, or you can say that method as comparing LHS and RHS. Comparison method, let me name it just for the sake of now as comparison method. So I will elaborate in a minute or so about what that method means. Second one is using modular arithmetic, to be precise. Modular arithmetic. And the third one will be uh, Fermat's method of infinite descent. Method of infinite descent. So we'll be learning about these three methods, which help us in showing or concluding that there is only a trivial solution or no solutions, especially no integer solutions to a Diophantine equation of any degree. So let's begin with this first method. So to begin, yeah. So the first method is the factoring method. So let's learn it through an example. So this is fairly a simple example, not not from any Olympiad or any other stuff. So for suppose we were given that x, y belongs to integers, and we got to find this integer solutions to this equation, or rather all integer solutions. All x comma y belongs to z. So how do we go about it? First of all, for any equation, you should try to find solutions. And if we are not able to, there might be a chance that that equation has no solution at all. And uh, teachers, I mean the questions in the Olympiads don't necessarily specify that this equation has solution or not, or prove no solutions. So you got to handle a double-sided sword. That is, so you try first to show to find some solution. If it doesn't, there is a chance that it have no solution at all. So similar is the case. You will try, if you try some questions, yeah, if you try some pairs, actually it will yield no solution. So how do we go about proving that this does not have any solution? So this equation, the question is 125x plus 5y equals 8. Now if I factorize this thing, that's what the first word of our I meant by the factoring word in the beginning. So if you can see, 5 divides LHS, right, left hand side. So 5 must divide the RHS. Uh, which is not possible in this case. 8 leaves a remainder of 3 when divided by 4, so not possible. So this equation has no solutions. This is how we go about proving that an equation has no solution, by comparing or and factoring some way. So this is one method. Now the second method is by modular arithmetic. We will use the same example, as I don't want to spoil any good questions or Olympiad level questions or Olympiad caliber questions. So let's begin. Here's the second method, which is fairly common in proving no solution to this method. Let's say that is modular arithmetic method. So those of you don't know about modular arithmetic, you can learn. It is very fairly simple concept. So the concept is basically, if you remember the Euclidean division algorithm, that any number can be written as in this form. Um, yeah, so this is the Euclidean algorithm. So same way, for example, let's suppose divisor is b. So we write this number as, in modular arithmetic, we read this as a is congruent to r mod b, or this is equivalent, a is simply r mod q. So both of these are equivalent statement. P and Q need not be equal. So take care of that fact. Now this is the fair idea behind modular arithmetic. You can learn about it more briefly from books and all YouTube videos. So learn and then again revisit this video to learn the concept. So the second method is like, we will use the same example. How to prove, rather this prove that there are equations, solutions to this question, or prove there are no solutions to this equation. So we will just go about taking modulo 5 both sides. So if this equation had solutions, this side would be divisible by 5, so it is leaving remainder 0. So 0 must be congruent to 8 divided by 5, that is 3 mod or modulo 5, which is a very common contradiction. So which is a contradiction. So this is not a solution. I mean, there exist no integers x, y belongs to z. Remember, I'm talking about integers. There might be some real numbers which satisfy, or rational numbers even, which satisfy this relation. But since we are talking about Diophantine equation, and this Diophantine concept revolves around integers, so we are specifically bound on integers only. So there are no integer solutions for that. So there are no solutions to this equation. I hope you got how I wrote this 3. So when 8 is divided by 5, the remainder is 3. So this is not possible. So by contradiction, we proved that our assumption was wrong, that this equation had solutions. Actually, this does not have solutions. So let us go to the third and most beautiful concept of infinite descent. So let's talk about Fermat's method of infinite descent. Descent. So when I do the concept, we'll come to know why some people coin this method as infinite ascent too, because in ascent we got to deal with the whole numbers, and in descent we got to deal with the fractions. So let's have a question. Say proving proving root 2 to be irrational. So this Fermat's method of infinite descent has two parts. One is uh, the main idea behind it is contradiction. We prove by contradiction that our assumption was wrong, and then we follow to our result of what we opposite result of what we assumed that was a contradicted result. So let's have this thing. So okay. So how do we move about this question? So let's assume for the sake of contradiction that is um, P over Q. Now P, Q are naturals because if it you can assume that to be um, integer, but either both of them has to be negative or positive because since 2 is greater than 1, so root 2 would be greater than root 1, which equals 1. So this must be positive. So both must have, I mean, p times q must always be greater than 0. That means both must have the same sign. So okay. So yeah. So if you assume now squaring both sides, we get p square over q square equals to, so multiplying both sides by q square, we get p square equals 2 times q square, which clearly tells 2 divides p square, as we learned in the method of comparison, the comparing method. So since p is an natural number, 2 divides p. So let's assume for some time p equals 2 times m. So what happens now? 4m square. I hope you know how I wrote this 4m from here. So this 4m square equals 2q square. So 2m square equals q square. So again with the same logic I used here, q equals 2 times s. Similarly, this goes when you replace q by 2s. Now we see this the original equation, that means here this one again reduces to root 2 equals m over s when I replace p by 2m and q by 2s to cancel out. And so again we come back to the same condition. So actually again this tells p and q are multiples of 2, I mean large multiples. So let p to be 2 to the power m times k. Remember k, I extracted all the powers of 2 from a p, so k must not be divisible by uh, uh, k must not be divisible by 2. So it must either be 1 or which is not divisible by 2, or any odd number. So if I similarly q must be 2 to the power uh, l times d. So if I rewrite the question as to the power p by q as 2 power m times k by 2 power m times d. Since these two are rational, so we can eliminate these two for some time. Now, first case we assume m is greater than l. So let me multiply this thing here and square it. Before multiplying, let's square. So I'm erasing this thing. Let's open a new slide. So 2 must equal 2 to the power of, I just squared both sides. Sorry, my mistake. 2 must equal 2 to the power of 2 times k if p equals, I might have assumed p to be something else, times k, and let q equal to the power m times d. So by p by q, this is p over q, 2 to the power 2m times d square. Since these two are rational, no need to consider them, or even considering doesn't make a difference. To the power m times 2 times dif across multiply equals 2 to the power 12 times k square. So assume first, if a greater than equal to b, I'm sorry, my mistake. Assume first that m is greater than equal to L. So if m is greater than equal to L, so 2 to the power 2m minus 2L must be either 0, that is 2 to the power 0, 1, or it must be, now even if this thing is 2 to the power 0 equals 1, this side is divisible by 2, but this isn't. You remember I said I extracted all the powers of 2 from p, so k must be 1 mod 2, that is an odd number. So we get one contradiction. Similarly, doing vice versa, we get, if I mean if m were to be, let me write separately, if m is less than n, I assume the case equal to and greater than, so let's assume the case less than n. No worries if you even consider this to be equal here, so you can try that way too. So this same equation, I'm not rewriting this again, would be like equals to, now this, since m is greater than L, so 2m minus 2L, I am, would be greater than 0 here, and an integer 2. That's why I wrote this. Similarly, then 2 to the power 2L minus 2m times d square. Now, sorry, oh, my mistake. So, yeah, this is k square. So this, these two numbers are not even. So this side is even, this side is even. But so we need to compare the powers of 2. So from here, we can see that either the power is 0 or an even 0 is an even number. So either this is even number or 0, but this is odd, you can see. So this is again a contradiction. So we get to a contradiction. So again the same contradiction or something uh, opposite, that is d square equals 2 to the power 2c times 2c minus 1 times k square if L minus m equals c. So this is again a contradiction. One side is divisible by 2 and other isn't. And also you might say that how is this a result? So this tells that our assumption that root 2 equals p over q was wrong. So, and this is the definition of a number to qualify as a rational number. So this root 2 doesn't qualify as a rational number, and hence by infinite descent, we concluded that there are no integer solutions to the question, or integer solutions. What the root 2 cannot be represented as rational fraction, rational number. So these were the ways. I hope you enjoyed the video, learned something, and you will apply some these cool things in the questions that will follow. Okay, see you again. Bye bye.